Welcome to Concrete 101. Today, we are going to discuss face mix pavers. In contrast with traditional thru-mix pavers, which use the same concrete mix throughout the paver, face mix pavers incorporate two distinct mixes in one unit: a base layer that looks a lot like a conventional paver, and a face layer that is usually 4 to 8 millimeters in thickness. In North America, face mix is now available in most markets, and many paver producers offer both traditional thru-mix and face mix choices. Both types of pavers deliver long-lasting beauty to hardscapes, and either one can be used with confidence. Here's an example of a face mix paver. We can see the charcoal color in the face, which concentrates the pigment, cement, and finer aggregates at the surface, which is the exposed part. It gets abraded by foot or vehicular traffic, takes the brunt of acid rain, UV rays from the sun, and freeze-thaw exposure. And the face is exposed and it's the part that we see. So it's not just a pretty face. The paver surface needs to handle many challenges and still look great.
Thanks, Ben. Now let's take a deeper dive into face mix concrete technology. As you can see in this example, the face layer has finer aggregates than the base layer, in fact a lot finer. This allows pavers and slabs to present a tighter and smoother surface, which is one of the main selling points for face mix pavers. So what about the base layer? The base contains larger aggregates for higher compressive and flexural strengths and improved durability. If we use a cold weather gear analogy to think about this, the shell outer layer on the ski jacket and the face layer on the paver both look good and are moisture and abrasion resistant. The liner underlayer in the jacket, or the paver base layer, provide volume for insulation, strength, and durability. Now that we know what our goals are, let's step back and review some basics for face mix raw materials and mix design. Water content. As always, it's important to maximize the water content for both face and base layers. This helps to hydrate cement, improve density, and reduce absorption. Face mix aggregate and cementitious materials. For conventional paver mix design, we would usually cover these raw materials separately. However, for the face layer, aggregates and cementitious materials are so interlinked that it makes sense to deal with them together. A common mistake is to assume that because a face surface looks tighter, that must mean that the surface is less absorbent. Unless you have super X-ray vision, don't trust your eyes. Here's an example of two pavers. If we compare these pavers with our human eyes, we might think that the surface on the left looks tighter and smoother, so it must be less absorbent. Not so fast. Let's go back to concrete fundamentals to understand what's going on. All concrete, including dry cast pavers and slabs, consists of aggregates glued together with cement paste. Within this matrix is a network of voids, or tiny air pockets, that are linked together with capillaries. The interconnected void and capillary network provides a pathway for moisture to move into and out of the unit. In a poorly designed or poorly manufactured paver like we see in the graphic, after only a few minutes, moisture can be wicked into the paver through the void network. The more moisture moving through the unit, the higher potential for efflorescence. Therefore, one of the goals of mix design is to limit moisture movement. Most face mix pavers work just as intended. Occasionally, we get called in to help with issues that are caused by these three mix design mistakes. Number one, using very fine aggregate in the face layer. This can happen when production is told that only the smoothest, most mirror-like surface is acceptable to customers, so production tries working with a mix design that is overloaded with superfine aggregates. Number two, adding too much cement to the face, again chasing that super smooth finish. And number three, using poorly graded aggregates, especially aggregates with only one size that do not pack well. To optimize the void structure and limit moisture movement, a useful rule of thumb for face mix design is that the amount of cementitious material should increase as aggregate size decreases. So the smaller the aggregate, the more cementitious materials we need. Wait up, I can hear you say. That sounds backwards. Nope, it's true. The finer the aggregate, the more cementitious materials we need. So what do we mean by fine? And how do we measure and describe what size aggregate we have? Average aggregate size can be calculated using the fineness modulus formula. Fineness modulus is an index number that represents the average size of particle in an aggregate sample and is used to get an idea of how coarse or fine an aggregate is. So the higher the fineness modulus, the coarser the aggregate. For reference, here are some FM examples of aggregates that we might see in dry cast concrete production. We can see the larger coarse aggregates have FMs in the 4s and 5s, and the sands or fine aggregates have FMs in the 1s and 2s. Since fineness modulus is an average, the same FM value can be obtained from many different particle size distributions. Bear in mind that FM is a broad tool that needs context and interpretation, but it's still useful. To find out more about fineness modulus and how to calculate it, check out the link here. Going back to mix design, let's repeat. The amount of cementitious materials should increase as aggregate size decreases. What this boils down to is that when using smaller aggregates, we need to increase cementitious fines, and this happens for two reasons. Firstly, to cover the increased aggregate surface area that results from smaller particles, and secondly, to physically block the smaller void and capillary structure that results from finer aggregates. So why are we going to all this trouble about capillaries? Here's an interesting concept, one that you may not have heard since high school: capillary suction. In scientific terms, capillary suction is the process of a liquid flowing in a narrow space in opposition to, or at least without the help of, external forces like gravity. Sometimes capillary suction helps us, for example, when we use paper towels to clean up a mess. And speaking of paper towels, in this experiment, we place paper towels in a colored liquid, and we get to see capillary suction or wicking in action, working against gravity. It's also interesting to note that, as you may have guessed by now, the smaller the capillary, the stronger the wicking action gets. Here's a capillary tube which shows again how smaller tubes have stronger wicking action than larger ones. Therefore, an unintended consequence of adding more cement may be that the void structure becomes small enough to get into the wicking danger zone, where any available moisture is efficiently wicked into the unit, increasing the potential for efflorescence. For optimal face layer design, it's important to understand that it is absolutely possible to properly size and blend aggregates to minimize moisture movement and still achieve a beautiful, smooth textured surface. Switching gears to the base mix. The most common problem is that for the base layer design is not coarse enough. It may surprise you, but a properly designed base layer should be coarser than a typical thru-mix design. Let's hear from our friends Farmer Bob and Farmer John to explain how this works.
Hey y'all, this is Farmer John, and just so you know, farming and making pavers are about the same thing. You need good soil in the cornfield. You need a good base to make it part of the face mix paver. You know, you can't have a good face if you don't have a good base. Just like corn won't grow without good soil. And by the way, the base doesn't need as much of that darn expensive stuff like cement and pigment. It's like I say before, if you ain't sweating, you ain't getting. Hey y'all, it's Farmer Bob here, and I don't know what that guy thinks he knows about dirt. You know, they don't call it face mix for no reason, and you can't eat good dirt. The face is the part that you see. The base is important, mind you, but you don't want it on the surface. The face mix has great colors and a smooth texture. And you know, just because you have a smooth surface doesn't mean you can't have absorption issues. You know, my base may look coarse, but it gets the job done. And you know, friends, that face mix needs to have the sand that fits well together so the absorptions are low. You know, my concern is someone over-compacting that base so that that face material can't properly stick to that base. And you know, friends, and I'm talking to you, we need to work together to make good face mix pavers.
Thanks, farmers. We have time for one more face mix fact. So here's a good one about unintended consequences. In this case, the unintended consequences of using more cement than we need. Increased Portland cement and other cementitious materials like fly ash or slag cement can deliver many positives for pavers and slabs, but there is an important downside to be aware of. Increased cementitious levels may lead to increased potential for efflorescence. So why is this? Increased Portland cement means more cement hydration reaction with calcium hydroxide byproduct from that reaction. Calcium hydroxide is an important contributor to efflorescence production. The second reason is that cementitious particles are very fine, and as we know, adding more fines typically makes voids and capillaries smaller, with more efficient wicking power and more potential for efflorescence. Once we're in the wicking danger zone, the best strategy is often to just double down and physically or chemically block the pores as much as possible, either with even more cementitious materials or with an efflorescence-reducing admixture. Admixtures. Most producers find that using a plasticizer in combination with an efflorescence control admixture delivers best results. Typically, the same admixtures may be used in the face and base layers, but may need to be used at different dosage rates. Consider the use of a retarding admixture in warmer weather, or if you're using white cement. White cements tend to have shorter working time. Retarders extend workability of the concrete and allow more time for mixing and molding operations. Each production situation tends to be different, so mix sequencing options should be trialed and optimized for best results.
So let's review what we learned about face mix. Face mix pavers have two layers. On top, a thin layer where cement, pigments, and fine aggregates are concentrated. Underneath is the base layer with coarser aggregates that provide strength and durability. When designing a face mix paver, remember that just because a face surface looks tight and smooth, the paver is not automatically better. Finer face mix designs can be more prone to efflorescence. That's due to the smaller pore structure wicking moisture into the unit. Optimized mix design and aggregate blends can prevent most of those problems. We also talked about the unintended consequences that can arise if we use too much cement. Face mixes with coarser aggregate blends, higher FMs, should contain relatively lower cementitious contents than face mixes with finer aggregate blends, lower FMs. Well, that's it for Face Mix Part 1. To find out more, check out Part 2, where we explore face mix production. Thanks for watching.